Hello and welcome to Measurements with the Gamma Scout in a nutshell. In the following episode, we will focus on measuring beta radiation and the proper selection of the absorber for beta measurements. Unlike alpha and gamma radiation, the configuration of the absorber is not that simple for beta radiation. First, we will discuss the origin of beta emitters. Some arise as products of the decay of naturally occurring uranium and thorium. There are more very long-lived beta emitters like potassium-40, which can be found in fruit like bananas. There is one very prominent beta emitter present in all bodies of all living organisms, carbon-14, which enables us to perform carbon dating on historic relics and artifacts. Another radionuclide with widespread presence is the radioactive hydrogen isotope tritium. It is used, for example, as a luminescent material in the dials and hands of wristwatches. Having radioactive materials so close to the body might raise concerns. However, we will soon explain why it is possible to utilize this radionuclide in a safe manner. As mentioned earlier, it is not possible to universally select beta-gamma shielding for all beta emitters to conduct appropriate measurements. In beta radiation measurements, decay energy is of greater relevance than in measurements of alpha and gamma radiation. Let us demonstrate this aspect for you. With our Gamma Scout, we will measure two pure beta emitters. This means neither of the radionuclides has a gamma emission. We will demonstrate measurements with the low-energy carbon-14 and of strontium-90 in equilibrium with its high-energy beta-emitting daughter, yttrium-90. We start by measuring our carbon-14 sample at a distance of 10 centimeters. We observe that the count rate exceeds our natural background level. You may remember that this is from 0 to 0.75 pulses per second. As we extend the distance to 15 centimeters, the count rate swiftly decreases to the level of the natural background. When we turn the lever to insert shielding for beta and gamma radiation, even at a distance of 5 centimeters, we observe that it has the same effect as for alpha radiation. The count rate immediately drops to that of the natural background. The scenario changes significantly with strontium-90. To illustrate it, we conduct a counting measurement with both sources, both at a 10 centimeter distance with the lever in beta position. The measurement time for all three readings, including a measurement of the background, was set to 5 minutes to ensure robust and meaningful results. As we can see during the measurement of carbon-14, the Gamma Scout recorded a number of pulses that does not deviate significantly from the background count. However, with strontium-90, there is a distinct rise in the number of recorded pulses. This result seems even more surprising when we consider that our C14 source has nearly 200 times higher activity than our strontium-90 source. Hence, we conclude that the effectiveness of beta shielding strongly depends on the energy of the emitted radiation. Therefore, we must be careful in selecting the proper absorber when measuring beta particles. This already gives a hint why a tritium watch dial worn on the wrist does not harm the underlying skin. Due to tritium being a weak beta emitter with an average decay energy of 5.7 kV, its beta particles cannot penetrate the watch glass and even less the metal casing. Similar to alpha radiation, the radiation emitted by tritium is absorbed by just a few centimeters of air and does not reach the Gamma Scout. Accurate measurement of tritium thus requires special instrumentation. And on that note, we bid farewell and sincerely thank you for watching. If you've enjoyed this video, please give it a thumbs up and subscribe to our channel to stay tuned for all our future content. If you have any questions or suggestions, feel free to leave a comment below. We look forward to seeing you again next time. Until then, take care and see you soon.